Great. So, I just want to thank you all for joining me today. We're here to talk about patient simulation, and if you've done TreeAge Pro modeling in the past, Markov modeling, and haven't done simulation, hopefully you'll see that it's actually very easy to kind of expand your model and make it more robust by changing it into a patient simulation model. So that's what we're going to do today. So, as you may have already know, HTA authorities and other uh, areas are looking for more robust and accurate models. And oftentimes, a simulation model is the best way to make the model mirror the disease process as closely as possible. Now, this won't be all models. Some models are perfectly fine or represent the disease very accurately as a standard traditional Markov model, but that's not always the case. There are times where incorporating patients and the process of simulation can make that model much more robust and accurate. And when are those cases? It's typically cases where either patient characteristics, I should say both, or patient characteristics or patient history has an impact on the way a model processes. So, for example, if you want a heterogeneous cohort and you have characteristics within the patient population that have impacts on, let's say, probabilities or costs, and those are important impacts, that ignoring those impacts is going to give you an inaccurate view of your decision analysis, then you need to incorporate patients into the model. Similarly, if there are patient events that occur, patient history that affects the flow of the model, you need to put that into the model as well. So an example of that might be gender, right? Patient characteristics would be gender, where maybe or age or something like that, where depending on the gender and age or BMI or whatever those are, you might be more likely to have some kind of event occur or less likely. And treating everyone as homogeneous cohort may be an inaccurate view of the whole disease process. From the patient history side, there may be some kind of event like a stroke, perhaps, that once you've shown that you are susceptible to that stroke, it may be more likely that you have another stroke. And if you don't have a way of recording the patient history within the model, then you're not able to make that model accurately reflect the increased risk that happens as those events occur. Now, those are just examples. They could be anything that involves a patient characteristic or some event that occurs to a patient that affects the model. But once you learn the technique of the simulation, you can do basically whatever you want within the confines of the model. So that's what we're going to do today, and hopefully you'll find that it's actually pretty easy to do. So in order to demonstrate this, we're going to start with a pretty standard Markov model, and then we will add to it, make it more robust, make it into a simulation model, and you'll see that you don't have to start over. Your model's already there. You just add the elements you need to what you already have. So in order to do that, I'm going to use some example models that I've pre-prepared. So we'll start with the heterogeneity via distributions. And we'll just take a real quick look at the model. And we'll see that there's not a lot to this that would be unique, and there's no simulation events in this, but it's just a standard Markov model. And I'm not doing decision analysis. We're just going to study as if this were one strategy within a decision model. So this would be the simulate. It's not a simulation. Well, it is a simulation model. Sorry, but we'll show how easy it would be to add these things. And it's just a standard 3-state Markov structure: mild, severe, and dead. I have events. You either progress or don't, and you can either recover, remain in a severe state, or die. Just standard Markov-like progressions. But there are some things in there that are unique to this model. But if you've built the Markov model, there's nothing here that should be unique to what you've done in the past. Now let's look at the elements in that model that are specific to simulation. And we're going to start with the characteristics. And there are a couple of characteristics, one of which is gender, and another is gene type. And under the assumptions of how this model was built, is making the assumption that we have demographics of the population, and we know that the the status or the value for those demographics affects things in the model. So what we've done with a table here, we have what we're going to eventually use this is to determine the patient characteristics. But we start with a table, and that table for gender is just 1 for female and 2 for male. So what we're basically saying is in our population, it's 55% females and 45% males. And we've taken that demographics, we've put it into a table, and then from the table, we have a distribution, disgender, which basically just all it does is say, okay, it's a table. From this table, assign a gender to each individual as they enter the model. So resampling per individual trial, patient would be a better word to put here. So every patient is going to get a new value for gender that's based on a table distribution that uses those demographics. So if I just test that distribution by selecting it and clicking this graph it button, it just does the samples, presents them in histogram, and we'll look at the histogram shortly. Just takes a minute. I haven't generated a graph yet, so so we see approximately, now I only sampled 1,000 times, so it's not going to be perfect, but approximately 55% of the individuals will have a gender of 1, that represents female, and approximately 45% will have a gender of 2, of male. So we've converted the demographics of the population, or the cohort, I could say, to the individual gender assigned to each person within the cohort. So we're not going to get each individual is not going to get 55, 45. Most of the individuals get this, and a smaller percentage will get this, and now they have that characteristic as they feed into the model. And we've done the same thing with gene type, where we say that the more aggressive gene type is number 1, because we have to represent it as a number, 30% of the time, and the less aggressive tumor type or gene type, 70% of the time. So we don't need to show that because it's exactly the same process, but we're converting the demographics to the individual characteristics. So when a person comes into this model and starts their process through their path through the Markov model, they're going to already have, each individual is going to already have a gender and gene type assigned. Okay? Now, you wouldn't bring these individual characteristics in the model if they didn't have any impact in the model. So let me just check for questions. I think there's a question. Oh, no questions yet. If there weren't any impacts, so we need to look at where those values affect the model. So if I didn't know where they were and someone gave me a model, I could really just go in here, find that distribution, and do a little find here. And it'll show me all the places where it's used. Okay, I'm just looking around. So this variable definition right here, P mild to severe, is basically saying that the progression is dependent both on the gene type and the gender. So let's take a quick look at that table. So where is that P mild to severe used? It's used right here. So this probability is dependent on the characteristics of the patient. And if I look a little bit more closely at that variable, P mild to severe, here's my definition, and it pulls it out of a different table based on the row of gene type and the column of gender. So let's take a quick look at the table. And we see with the more aggressive tumor type, let's say you have a female that comes to the model with a more aggressive tumor type, their probability of progression is 22%, whereas a male would be 20%. And if they had the less aggressive tumor type, a female would have 16%. And if it's a male, 14%. So what we're basically saying is that the characteristics that the patient brings into the model do affect the movement through the model by changing the progression rate. So mute. I just have to mute everyone. Okay, good. So that's how the characteristics come into the model, and that's how they're used in the model. And now we can run it. So if I just go back here, and I would not run these cohort analyses because those would ignore the patient characteristics. I can't treat this as an expected value calculation with a homogeneous cohort. I have to instead running this microsimulation, which is running patients through. So I'm going to select that Markov node, click this simulation, and I'll run 5,000 patients through. Let that go. Now my patients are running through the model. And what I end up with is a mean value for the entire patient population. That is what I would use for decision analysis, this mean qualities of 13.25. I'm not going to do decision analysis. That would be a subject of another webinar or different topic in general. But this would be the value that feeds into the analysis if I were doing decision analysis. But what I've really done is I've really run 5,000 patients through, right? And they all experience a different quality. Okay, so they had a gender, they had a gene type, and that person got this quality. Now, somebody else with the same gender and gene type is going to have a different experience, right? Because they're all doing a random walk simulation through the model. So just because the characteristics are the same doesn't mean the experience will be the same. But the experience is affected by these characteristics. So I wanted to show you that. And also, I wanted to show you something over here in this console where I've used the debug function in the model by specifically selecting to look at the probability of progression. And I can see, here's the debug output. This person, trial number 1, had the more aggressive tumor type, was a female, so they got the highest probability of progression. Whereas if I just looked at some other person down here, person 4, right? Here's someone with the lowest one. They had the less aggressive tumor type, and the male, which was less susceptible to disease, so that person had a lower progression probability. So I'm just showing you in the debug output the ability to see how those characteristics affected the progression probability, so that gives you some power, not just to build it into your model back here, but to see it in place and make sure that it's working as you wanted it to, as you designed the model. Okay, so let's move on to the next piece, which is a little bit different. So we basically, in this example that we just did, we assigned the characteristic based on demographics. You might instead have a patient database. You might have information on individual patients that you could use as inputs in the model. So I want to show you how you can do that. So I'm just going to close this model and the results. And I'm going to open up the second model here, Heterogeneity via Bootstrapping. And you'll see it's going to be the same two characteristics, but they're going to be assigned in a different way, under the assumption that we have a patient database, that we have some record of people who've come to the hospital, let's say, with this problem, and we know that their individual characteristics. And the advantage of that approach is you don't just have the characteristics assigned independently. You know the kind of breakdown of the types of prototype people that come in with this problem. And the first person you happen to come in had a gender of 1 and a gene type of 2. But these are all people that actually experience the disease. Now, presumably you'd want to have more than 100, but for this example, I have 100. And each of these is a real person, and we're using that real person's individual characteristics to feed into our patient simulation, our simulated patients as their characteristics. So what I'm going to end up doing when we run the model is every one of our simulated patients will be randomly assigned any of these 1 to 100 profiles, which were real people. And if they happen to be assigned profile number 8, that's going to be the less aggressive tumor type and a male. So that's how we'll do it. So here's all their characteristics. How do I assign them to the individuals? I need a distribution for that. All it is a uniform distribution that assigns an integer value 1 to 100, right? Because that matches against our profile table. So our profile table had 100 real patients. I'm just assigning anywhere from 1 to 100 to each one of our simulated patients. And then when that individual comes into the model, they'll have the characteristics that came from a real person. So this is a way to use real world data to inform the simulated patients that enter your model. So now it's input data, right? You're not inputting the final cost and the qualities. You're using this as the characteristics and then letting the model calculate what happened to them in terms of how long that person lived or how many qualities they accumulated on the path through the model. So I do the same thing, and the impact on the individuals is the same. It's still built into this mild to severe progression probability. So I can just run it again, run 5,000 people through. And if we look at this a little bit differently, look at the all data report, this is the individuals, and I can see simulated patient number 1 was assigned profile number 28, which gave that person these 2 characteristics, and then they passed through the model and then ended up with 17.9 qualities. So every one of our individual simulated patients got a different, maybe not unique because we have 5,000 and only 100 real patients, but was randomly assigned one of the characteristic profiles, and then that drove their characteristics, and then they proceeded to the model. So that's just a different way to introduce the characteristics for a heterogeneous cohort into your model. So that's enough for now on patient characteristics, but let me just check and see if there are any questions on what we've done so far. I don't believe so. No questions. So we'll go ahead and move on to the patient tracking. And this is the patient history. Now I probably should quickly look at out here, and here's the tracking from the new model, and sure enough, it's the same thing. It's the same. The characteristics were assigned in a different way, but again, they affected the progression rate. So there's not really a lot to see there that we haven't seen already. So I'll go ahead and close that. But now I want to talk about the patient history, because that may be even more important to bring to the model. May I ask how the distribution variable was? That was a good question. May I ask how the distribution variable is used in the model? It's used in the same way. Let's look at the model again. It's still the variable properties, and this is just an example. It's still the same probability of the progression rate being dependent on the gene type and gender. But I don't think I did miss one thing that I wanted to show you, which is how did we get the T gene type? I put it in a tracker right here as they enter the model, right here. I set tgender equal to, thank you for pointing this out because I did miss this. So I assign the gender from the patient data table based on the profile that was assigned, that's the distribution, and column 1. And the gene type, same table, because that's where all the individual real world data is, same profile, but column 2 has the gene type. So I had missed that. So when a patient enters the model, the first thing happens is they get assigned a profile. And then as they go into the first state, I take that profile and assign the gender and the gene type to that individual. And you might say, well, why are you putting it in trackers? If I do that, I can do some filtering later and look at the results for, let's say, gene type 1 separately from gene type 2 in case I want to see if subgroups have different results. So thank you very much for that question. That was really very helpful. Okay, good. So now let's get on to patient events. So there is one event in this model, and it's in both of those two models, that we're making we're tracking, and we're using that patient history to change things. And where you see it is right here. This is a tracker. T progression count equals T progression count plus 1. So when any patient reaches this progress to severe progression node, we add 1 to the count of progressions. Okay, so we're basically just recording how many times that individual's progressed. Now, we wouldn't do that if we didn't care. So there's 2 possibilities. We just wanted to count it because it's an interesting output, which that may be, but we're taking it to the next step of that actually has an impact. So where's the impact? I can look at the trackers. And here's the progression count, right? Here's the progression count. Here's where it's set, and here's where it's referenced. So we're basically saying the probability of going to severe to dead is affected by the progression count. So let's look a little bit closer at this And what this choose function is doing is it's taking the progression count. The minimum of that are 3 because the value doesn't change beyond 3. The probability isn't going to change beyond 3. And it's using either the first, second, or third parameter that we have. So let's look back at the model for a second. So basically saying the first time you progress, your probability of dying is 10%. The second time you progress, it's 20%. And the third time you progress, the probability of dying from the post-progression state, the severe state, is 30%. So the only way we can do that is by knowing how many times we've progressed. So you wouldn't just make this up like I did for an example model. You would be studying the disease progression, and you'd have determined that if you progress and recover and progress again, your disease has gotten worse, and your likelihood of surviving the second progression is worse than the first time. So even though I just made this up, that's what I'm trying to mirror in a real world example of each time you progress and you get down to severe, your chances of death are worse than they were the prior time. And the only way you can do that in a model is by actually recording how many times you progressed and then integrating that progression count into this probability. So the reason for the min function is we're saying it goes from 10% to 20% to 30%, but then it never gets any worse than that, right? So we just have 3 values. If it's your first progression, you're going to get the 10%. If it's a second progression, you're going to get the 20%. That's here. The third progression, you're going to get 30%. And if it gets beyond that, you're going to keep using this severe value and continue from there. So let's go ahead and run the model and see if we can see that in action. So I'm going to run it again. In fact, I've already run it. So I've got the results here. And if I look at my progression count, right, my P mild to severe is not what we're looking on, but here's someone that progressed, right? This is trial 1, the first patient, going through the progression node, and their progression count has changed to 1. And when they came down here and were experiencing the likelihood of death because they'd only had 1 progression, their probability was 10%. Okay? Now, if I go down a little further, eventually I should get to somebody with a progression count of 2. Just got to look. And if I have time, here's someone who got to the second progression, right? This is trial, same first person, but in stage 13, so 13 years in the future, had the second progression. And now, from the severe state, the probability of death has changed to 20%. So we're seeing that the event in the patient history has changed the risk moving forward. And that's what the integration of patient history is all about, is being able to use events that happen within the course of that patient passing the model to affect risks or probabilities or costs or utilities in the future. And that's what we've shown here. Okay. Now, I do want to show you a little bit of how I debug these things, because I specifically wanted to show those 2 things. So if you look at the model, back in the model, under variable properties, you'll see this debug out here. Is basically I wanted to show you the calculation of those specific formulas. So I marked those for debugging, and that's how I got the output here. Because if I had everything output there, there'd be too much data. It'd be too hard to find what I wanted. And so there's a technique to just say, I just want to see the recording of specific elements so I can make sure they're working. And when you're done, you can just turn this off. You don't have to keep it on forever. It's just a way to check things. Okay, so that's the way those 2 things are. The in terms of the patient history and the patient characteristics. I do want to show you one more thing here on filtering, that I could, for example, take this average of 13.27 and say, I really only want to see the values for gene type 2. So I could say, I want to filter this heterogeneous cohort and only show me the data for gene type 2, and you see the mean has changed a little bit. So you can once you have the heterogeneity in the model, you can say, well, now I want to look at a subgroup within the overall cohort and say maybe I could that subgroup could benefit from a different intervention or treatment. So you have the ability to kind of back out the heterogeneity to a certain degree and focus on specific subgroups within the overall cohort, which provides some power as well. The final thing, when people use simulation, sometimes they want to stabilize the results so they can run it over and over and get the same results. You don't want to do this too early because you want to make sure you have enough patience in your model to make sure that your estimates are accurate. But once you've reached that point and your estimates are accurate, you may want the people who receive the model to be able to get repeatable results. So a way to do that is to go into tree preferences and go down to analysis settings, Monte Carlo options, and seeding. And the fact that I've checked this box means that every time I run the analysis, I'm going to get the same results. And that can be helpful when you want to share your model with someone else and they're getting slightly different results and they're getting confused by that. If you just use the seeding, then the results will be repeatable. Even though there's randomness within the model, you're basically using the same random number sequence, so the results come out the same. So that's really all I had to cover today. In summary, it's fairly straightforward to integrate patient characteristics and patient history into your model to make the model more robust and reflect reality more accurately. And it doesn't mean you have to start over. It doesn't mean you have to start with a new model. All you do is just integrate the characteristics in on the input and then use them in some calculation. And the same thing with the patient history. You just choose what you want to record and then how it affects the future paths of the patients in the model. And that's all I have for today. So I'll just go back and see if there are any questions. We have the question, what are the different threads? So when that's really a computing question. So most computers have multiple processors. Modern computers, in fact, anything that you buy today would have at least 2, probably 4 or 8 processors. And what TreeAge Pro tries to do for speed reasons is use all the processors for the patients so that it runs faster. So if you can send some patients to processor 1, 2, 3, 4, 5, 6, 7, and 8, you spread the load and the analysis finishes quicker. But in the output, in the console output here, sorry, not that one, this one. If we put them all together, and I have it single threaded, so everyone's going to the same thing. So I specifically only ran one thread. But what you don't want is the different output from the different processing chains to be overlaying each other. So you have half of patient 1 and half of patient 2 kind of on top of each other, and you can't read this output. So this is basically just, I have six processors, thread 1 through 5. I'm only using thread 0. That's why these are all blank for this example. But if I had a big analysis, I'd use them all, and I'd want to be able to see whatever patients were used on the first processor separate from those on the second processor, so they're not, so that the output isn't garbled. And that's what that's about. Is there another question? What is choose? Okay, so thank you for asking that. The choose command is a function. Let me just make an easier option below this. So if you use the choose function, has several arguments. The first one always returns a positive integer. In this case, 1, 2, or 3. And you notice I have the min here to make sure it gets beyond 3. So this is going to be 1, 2, or 3. If it's 1, it returns this first. The first argument after that index. If it's 2, it returns this one, and if it's 3, it returns this way. It's kind of a way of having an if inside an if without it getting confusing. So basically, choose is the first argument always returns a positive integer, 1, 2, or 3. If it returns 1, you'll get this one. If it returns 2, you'll get this one. If you return 3, you'll get this one. So it's almost like a little table lookup, but it gives you the ability to have actual parameters that you could run sensitivity analysis, and not whereas a table just has numbers in it. So any other questions? No? Okay. If we're all set for today, I want to thank you all for joining us. As always, we do webinars approximately every month, and the schedule is at www.treeage.com/webinars, and I hope that you'll join us again sometime in the future. Thank you all, and have a great day.